We have massive problems in special relativity with what? With definitions. There are no definitions in mathematical physics, so you can't arrive at any conclusion. You cannot understand what these people are trying to translate, okay, from their math to the ordinary language. And, there's a problem there because people want to know in regular language what happened. And these people are translating their mathematical concepts and trying to do the physical interpretations with their mathematical concepts. So they bring in words such as field and energy and mass and time. And the other person says, well, I didn't understand squat. Yeah, he didn't understand squat because the presenter, the mathematician, he didn't understand squat. Okay, he says, well, I understand it in the world of math, but I cannot translate that into the language of ordinary speech. Of course not, because the language of mathematics, right, which has nothing to do with physics, right, mathematical physics, that's a contradiction in terms, right, an oxymoron, right, mathematics is, a descriptive, a quantitative language, if we can call it a language. Some guy was telling me that it's not even a language because the language has to express itself, it has to be able to give you about causation and explanations and theories. And he's right to that in that sense. All languages, I don't care if it's Chinese or Greek, can express thoughts and explain things. Math cannot explain. Math is a language that has no power. In fact, it's impossible for it to explain anything. It can only describe. And these people are trying to explain how the universe works because they do give you a physical interpretation and explanation known as a theory, right? They call it a theory even though it's not a theory. There are no theories in mathematical physics that are rational. Why? Because they're trying to do the theory, the explanation, the physical interpretation with mathematical concepts. They're moving concepts around. They're saying, oh, the mass moved this and the field vibrated and the wave came down to us oscillating up and down. That's the problem. The problem is that the language it's not even a language, but assuming it's a language, a descriptive language. That's all it is. It cannot explain. So why do the mathematicians who call themselves physicists cross the line into physics and try to give you an explanation, a physical interpretation of how the universe works? Why are they looking for a theory of everything, meaning how you merge or unite light with gravity? Meaning, you have to visualize something. You have to say, how is gravity like light? There has to be something that mediates both. And for that mediator, it has to be a physical entity. And they're not thinking in those terms. They're looking for an equation. And so we have a problem because these people are the wrong people to be doing physics. Okay. But everybody thinks they're intelligent. And they're not. They're not very intelligent because they've come up with all this poppycock with dark matter, dark energy, and now they're in a hole because they cannot explain anything. They say they use dark matter as a spirit that they introduce into their physical interpretation. They have these invisible spirits like dark energy, dark matter, black hole, wormhole, etc. Right? They even have virtual particles. They come in from the void. These are all spirits. It's the religious people of the old who have become now the mathematicians, and they think they're scientists because they're explaining all this stuff with these inexistent, invisible, dark, black, spirits. We can't see them, we can't touch them, but they're there, right? They tell the astronomer, go look for it. Go look for a black hole. What is it? It's a zero-dimensional nothing. Okay, I'll look for it. Let's see if it shows up on my telescope, okay? Okay, so what was the problem? The problem is definitions. It starts with the problem with definition. They never had a definition for the word mass, just like they never had one for time. And here we have a difference between good old Newt, right, and good old Einie. You can see that these two guys had a different notion. In fact, it's Einie who created a different notion of mass. He had to, in order to get his special relativity so-called theory, through, which was a mathematical description anyways, okay, because the theory part is totally irrational, has no place in science. And so this comes from the Wikipedia. It says, the notion of mass as a property of an object from Newtonian mechanics does not bear a precise relationship to the concept in relativity. No, it's not even precise. It's not even comparable. They're talking about two different things. Newton was talking about quantity of matter. Quantity of matter is something you count. Okay? What was Einstein talking about? He was talking about weight, and weight we measure. And actually, it's not actually weight, as we'll find out in a minute, but that was the closest thing you can come up with if you're talking about what Einstein was referring to when he was talking about mass, relativistic mass, all this stuff. He was talking about weight, but a different form of weight, and I'll get to that in a second. So the Wikipedia continues, says, relativistic mass is not referenced in nuclear and particle physics. Right, because they can't. You know, and they only show it in popularizations. Yeah, because they can only talk about nonsense. And so they say, we'll feed this to the public, popularizations. And that's what the public reads anyway. They don't read the so-called scientific literature, the mathematical literature. They don't read that. So you have to kind of translate it in the way you want it for them. And you can always have the excuse that, we cannot put our equations exactly in ordinary speech. We cannot translate that exactly because Father Universe speaks a different language and he doesn't have to conform to our way of thinking. And that's philosophy anyways. And they go on through all these excuses, right? Okay, so what's different between Newton and Einie there, right? Einstein, right? This is from Newton's book, Principia, right? Mathematica. The quantity of matter is the measure of the same, arising from its density and bulk conjunctly. In other words, Newton defined, in his mind at least, he defined mass as the quantity of matter. And we can all more or less understand what he's saying. We don't have a unit for the mass. We don't have a unit of mass. We could count units and say, it's 10 units of mass. In other words, 10 x's, whatever x is, right? And so, but he had this notion that, mass is just a quantity of matter. And he said, is this quantity that I mean here, hereafter, everywhere under the name of body or mass? Okay, so that was his definition of mass, the quantity of matter, essentially. Weight, what was weight in his mind? He says the quantity or amount of matter being moved. Now he's talking about the motion, okay? And so, he was referring to the fact that, an object falls to earth, right? Like a stone or whatever to the center of the earth. And he says that motion, that's what he was calling weight, meaning gravitational acceleration. So he had this notion. This is the one he put forth. Einstein had to change that. Not only Einstein, Poincaré, Lorentz, all these people had the same notion. They had to change all that because they couldn't make sense of Newton's straightforward language. And the main reason is quantity of matter, right? Like a ball, quantity of balls. You have 10 balls, that whole thing is called one body, and we call that a quantity of matter. We can all understand that. But mathematicians, they don't work with objects. They don't work with objects at all, and that's where they failed. All they do is they work with numbers. And so they had to start talking about the motion, the inertia, the energy. They started introducing all these weird, undefined concepts, which they later on gave to the public. And then the public today talks about energy and force and field and time as if it were, common language. And nobody understands what they're saying. Nobody ever, pinpointed what they're saying. And so Einstein had to change this mass, a measure of a body's inertia. Now, Einstein understood inertia. He did talk about inertia also. He defined it in his, right before the scholium, in his first definitions, where he talks about mass, right? So he already had a notion of inertia. But that's what Einstein emphasized, the body's resistance to any attempts to change its velocity. Okay, now that has a double meaning. This is what we're going to look at here when we talk about mass. It has a double meaning. There's two meanings to this, okay? The first one is gravity. We all understand that. Body falls to earth, right? And we call that gravity. But is that mass? No, we call that weight because we're saying it's the acceleration that the Earth, for some reason, magical reason, it's pulling, apparently pulling, right? Some believe it's pushing, but it's pulling on the object, or the object is falling towards the Earth, right? So there's an acceleration, 9.8 meters per second square. That's the, 9.8 meters for every per second for every second that goes by. So it's going faster and faster and faster. Okay, but that's weight. Okay, so Einstein's referring to weight. But where's the catch? Well, what if you're going sideways? Now you're not falling towards the Earth. Now you're falling towards the side, and that's not gravity, is it? So, well, we'll get there. Give me a second here, okay? We'll clarify that. Okay, but that's what I'm referring to here. Okay. Anyways, here we have from the Wikipedia. It says the word mass has two meanings. As always, everything in mathematical physics, mathemagics, as we call it, has many meanings, especially to confuse not only the mathematicians but anybody who listens to them. Okay, says has two meanings in special relativity: invariant mass, also called rest mass, right? And is an invariant quality, meaning it doesn't change, right? Which is the same for all observers in all reference frames. What are they talking about? They're talking about if the thing doesn't move in your local frame of reference in front of you, right? You're not traveling, even if you're traveling 1,000,000 miles per second, it doesn't matter. You have this object in front of you, this rock, right? It's standing still. It's not moving with respect to anything around you. That's the rest mass. What are they talking about? Quantity of matter. That's what they're talking about. They're saying this is how many atoms, assuming if we could take the hydrogen atom, for example, and use it as a unit of mass, we would say, okay, this rock has a gazillion hydrogen atoms. That's the mass of the object. Instead, what we do, we take the rock, we put it on a scale, and we weigh it, and we say, oh, it's so many kilograms. So they weigh it, they measure quantity of matter. And that's wrong. Quantity of matter means you count. You count every unit, whatever the unit is. You designate a unit, say so many units. That's mass. But see, they couldn't do that because they can't count every atom in a rock or in anything for that matter. And so what they say is, what we do is we measure. We measure, we put it on a scale, and we tell you how much it weighs. And that's the quantity of matter in terms of weight. So while the relativistic mass is dependent on the velocity of the observer. So they're saying that, if you've got an observer moving with respect to you, you're in your reference frame, in your frame of the universal movie, you could say. You're in your frame, right? In your frame of reference. You're standing still, what is called proper mass, right? And you hold the rock in your hand. The guy that's moving, he measures the weight of the rock at a different value than you do, because they're looking at the speed of light, how it intervenes in there. See, the speed of light is in the equation for mass contraction, mass increase, right? So this is important to notice. But again, quantity of matter is counting all the marbles. Weighing is, putting them on a scale and giving you a value such as a kilogram or a pound or whatever. Okay, so we have to understand the difference between counting and measuring first, and second, between quantity of matter and what Einstein referred to as relativistic mass. Okay, so here we have a situation, okay, so that you can more or less visualize what I'm talking about here, okay? We have an elephant, two elephants, in fact. We have Dumbo-Stein and Frankenstein, okay? And we have these two elephants. They're twins. They both weigh exactly the same, 5 tons each. In fact, we don't have to have two elephants. We could have a single elephant and just do the experiment with a single elephant, okay? But one on the left is falling at a quarter of the speed of light. The other one falls at 0.95% of the speed of light. So Frankenstein there, he's going to fall a little faster than the guy on the left. Now, the guy on the left, he's falling towards a small star, and the other guy is falling to a big star, okay? And so we put a scale on, somewhere on the surface of these two stars. Yeah, Frankenstein is going to fall faster. So the question is, has the mass of the elephants changed? And the answer is no. For every frame of the film, the elephants have 5 tons. And the one on the right is falling at a faster rate simply because he's falling to a bigger star. The weight has changed because as he's falling, he weighs more at different locations than the guy on the left. Okay, the guy on the left is falling at a slower speed, slower acceleration. So at any frame of that film from 632 onwards, the guy on the right is going to weigh more. But the mass of the two elephants is always the same. We have a star that's changing the velocity of these two objects, the elephants, and their mass doesn't change. So, what was Einstein talking about? And again, what he's talking about is the fact that there's three kinds of masses invented by the mathematicians, beginning with Newton. And here it is. This is the first one. Newton has this quantity of matter. That's where he started, right? And then he's got this downwards mass, right? And he calls that gravitational acceleration or weight, okay? And you can see the equation, if we turn it around, his gravitational equation, the mass of the object is going to be equal to everything that's on the right. Force, distance squared over gravitational constant g, mass of the Earth, right? Now, of course, if you change the mass of the Earth for mass of the moon, which is 1/6 of the mass of the Earth, well, that mass of the observer is going to be less, okay? So you can see that the mass changes, right, if we have a different object attracting it downwards, right, we'll call downwards towards the center of an object, right, like to the center of the Earth or to the center of the moon. But Einstein developed a different notion, and he's talking about inertia, not really downwards. It's like he included all of them, the downwards as well, where he fails. But he had this one sideways, which is not really gravity. It's like you moving sideways. And the problem with that is he's talking about the velocity of light. He's introducing the velocity of light in that picture. And you can't do that here on Earth. To be able to do what he's trying to do, you got to do it out there in space, because you're going to talk about the velocity of light sideways from the observer's point of view. But what are you staring at? You're staring at gravity, because the object is falling towards the sun or a star, like we just showed, the elephant falling, right? And he, from a point of view of gravity, he's falling straight downwards towards the center of that object, okay? So the fact that the observer is seeing the whole image sideways, Einstein got confused and he thought that, that's not gravity, or he can talk about the inertia or the acceleration or the change in velocity, but he's talking about gravity because the object can only fall in outer space towards another celestial object, such as the Earth, the moon, or the sun, or any star for that matter. And so this is the issue. The issue is there is really no three notions. But if you take the second notion there, the weight, and you take the third one there, the relativistic sideways, both of them are gravity. Both of them are gravity. So there's only two notions. One is weight, and the other one's mass. And mass has nothing to do with inertia, and has nothing to do with motion. Mass is simply counting atoms, the number of atoms. In fact, here we have a very trustable source, reliable source, and that's the American Museum of Natural History. So they tell you what the difference between mass and weight is, so that nobody has any doubt. It says mass and weight may seem like the same thing, but in fact these two measurements are very different. Mass is the total amount of matter. Newton, sounds familiar there? Or stuff in an object. Weight is the force of gravity on an object, on that same object. Okay? Mass always stays the same. Yeah, tell that to Heine. But weight can change depending on how much gravity is acting upon an object. Okay? So, we have all these contradictions because all these people talk about mass and weight, and they say, they teach you in high school or even in college, they say, look, mass is not weight, weight is not mass. Okay? That's first of all a lie, because we have no way of distinguishing between the two. And both of them are measured, which is a problem. Like if you take the grand kilo, which used to be the standard kept in France, right, of the kilogram, was there since at least the 19th century. they had this block of iron, and they said, this is the grand kilo. This is the kilo for the whole world. This is the standard to which you have to measure your standard. Okay, if you want to have 1 kilo. Okay, fine, no problem. If you take that grand kilo, right, here on Earth, and you take it to the moon, what weighs 1/6 as much? Okay, so it's 1 kilo divided by 6, about 15, whatever. Okay, so what's the issue? The issue is that has the mass changed? Has the number of atoms changed? And the answer is no, obviously not. It's the same kilo standard here, the same kilo standard on the moon. They just weigh differently. And that's what, they teach you. They say, well, that's why mass is not equal to weight. But it turns out that, the mass has also changed, because the way we determine mass is by weighing. We measure it. We don't count atoms. See, if they counted atoms when they left the Earth, they said, well, this grand kilo has exactly 1 trillion atoms, right? Assuming, right? And we take it to the moon, we still have 1 trillion atoms, so the mass has not changed. But that's not how they do it. They measure mass. And they said, measure 1 kilo here, and it measures different over there. So the mass has changed. And it has changed just like weight has changed. The weight here was such 1 kilogram, and over there it's 1/6 of a kilogram. So mass is equal to weight unless the mathematicians can find a way to measure, to count atoms for mass. For weight, we have no problem. We measure it. No big deal. But for mass, you gotta count atoms. And they don't count, they measure. And that's where the problem is. So that's why they have never defined mass or weight in a rational manner, and they cannot use them consistently. That's the whole problem. So yeah, if you were able to define mass scientifically, then special relativity would go down the drain, especially in the case of mass. You say, well, it's the quantity of matter. Special relativity can't live with that, because what they're trying to tell you is that this thing increased in mass, that traveled close to the speed of light. And you're saying, well, what happened? Did it acquire more atoms? Did more atoms get created in the interstices between 2 atoms? What happened there? How did it increase its mass? And the answer is, well, it presses down harder on the scale. That's called weight. Sorry. Whether you do it sideways or downwards, it's called weight. In other words, gravitational acceleration. So that's the problem. That's where the whole thing is. But then, if they would have stopped there, but they had to go further, because again, they couldn't live with the speed of light. They had to exceed the speed of light, the mathematicians. So they began to find ways, mathematical ways, to circumvent the speed of light. And of course, they always succeed, and all their papers get published. In other words, they get peer-reviewed and published. You don't publish a rational one, because if you put a rational one and you go against special relativity, it doesn't get published. The peer reviewers reject it. But if you go in there and you say, look, mathematically, I can show you, then we'll accept that paper. And they publish those papers, and they don't allow anyone to criticize those papers, because, if you criticize them on the basis of rationality, they don't like that. They say that's philosophy, and that they don't understand the explanation either, and that Father Universe doesn't have to conform to our way of thinking and all this other nonsense. They just want equations. And that's a problem, because this is not an issue of equations. It's a question of what is and what happened actually, really, right? That's what it's all about. And so they created this thing called negative mass that we talked a little bit about the other day, and they used all these little things with which they circumvent the speed of light. And they said, hey, we can go faster through a wormhole, or we have the tachyon that comes in from the future so fast, that it comes from the future. And we have the warp drive, we reduce up front, raise in the back, and you go faster than light. They have all these mechanisms, right? And that's what, and you might say, well, this is all speculative. No, it ain't. Okay? It ain't speculative. Believe me. If it's published every day, right? You see countless papers on all this stuff. It's no longer, for them, it's real. For you, it might be speculative. For them, it's real, because they work on it. You're paying for these people to develop equations for this garbage. So don't tell me it's not real. It's real. It's hurting your pocket, but you just don't know about it, okay? And here's one fellow that proves my point, okay? His name is Jeff Landis, and he worked at NASA for several years. He was trying to develop a way of traveling faster than the speed of light because he needed that in order to reach Andromeda. Proxima Centauri, the nearest star, right? And so he was developing an equations or a technology in order to get us to the nearest star. And he was there for several years, I don't know how many, and eventually NASA cut off his funds and I guess promoted him. It's called career redirectioning. You know what I mean? Yeah, they promoted him. They canceled his program because it was wasting money. He couldn't come up with a solution. And so he went out of business at NASA, and still, even to these days, he's still trying to figure out a way of traveling faster than the speed of light. And he joined the crew of all these people who try to go past the speed of light. And here's this fellow, and he'll tell you a little bit about negative mass because that's what's required to travel faster than light. You need to have negative mass. And you say, well, that's speculative, Bill. No, it ain't. And listen to this guy so that you understand that it's not speculative, okay? You're the one who's in the wrong here. Here it goes. I like the fact that he's in the Wikipedia. You can find him there. And he was at the 75th World Science Fiction Convention. Yeah, that I believe. And Landis writes, what? Hard science fiction. What is hard science fiction? A category of science fiction characterized by concern for scientific accuracy and logic. Oh, yeah. And so he talks about negative mass. Okay, and so this is what he's got to say in the paper he wrote. He says, as first analyzed by Hermann Bondi in 1957, matter with negative mass is consistent with the structure of Einstein's general theory of relativity. I thought it wasn't because Einstein was opposed to it, but he says it's consistent with it. Okay. Although initially the concept was considered just a theoretical curiosity, right? I didn't even think that it would qualify for that. It would not qualify under science or even worthy of study at all. But he says negative mass or exotic matter is now incorporated into the body of mainstream physics in a number of forms. Okay, so is it speculative? Think again. Negative mass has a number of rather non-intuitive properties, which results in possible applications for what? Propulsion requiring little or possibly no expenditure of fuel. So they're not going to do it with physical things like, booster rockets and anything like that. No, they're going to do a mathematical calculation and show you how something with negative mass can travel faster than light. Yeah, no kidding, because it's an equation and they just put a negative sign. That's what they do. So it says negative mass, or more strictly, violation of zero energy condition, In other words, can you have zero energy or negative energy? Well, that's more or less what negative mass is, negative energy, is also a requirement for any proposed faster than light travel. Okay, keep that in mind. Faster than light travel demands negative mass. Okay, and that's what these people are writing, and this is what you're paying for them to do research on. Okay. This paper presents the basics theory of negative mass, the ways by which it can manifest in contemporary physical theory, and the counterintuitive properties that result, including possible uses for interstellar propulsion. That's what they're interested in. They want to see how you can get the nearest star by traveling faster than the speed of light, because you cannot do it traveling at less than the speed of light. For that, you need negative mass. Negative mass has moved from the theoretical curiosity to a concept fundamental to the contemporary understanding of physics. Okay? And I have to give you the second part of that because it's just priceless. Okay, here it is. 1957, Hermann Bondi pointed out that matter of negative mass is not inconsistent with the structure of Einstein's general relativity. Such negative mass matter would have odd properties. No kidding. Contemporary theoretical physics incorporates forms of negative energy. Okay, meaning negative mass. Physicists use the phrase mass, and here it is, to mean several different things. Yeah, no kidding. They have all these different notions of mass, trusting in general for the right meaning to be clear in the context. In other words, they don't define mass for you. They say, look, you'll figure it out by the context, what we're talking about. That's a good way of selling a used car, right? Negative mass reacts oppositely to all forces. Oh, force and acceleration are opposite, okay? Thus, when you push on negative mass, it moves towards you. Okay, we had that the other day where I throw the ball and the object you hit comes towards you. Well, this is what they're talking about. They're saying that you throw negative mass at something, or you throw a ball at something, and because it's made out of negative mass, instead of pushing you away, it gets closer to you. When you pull on negative mass, it moves away from you. The force of talk about your rationality, right? This is surrealistic now. The force of gravity on a negative is opposite in a gravitational field. So when M is negative, gravity pushes instead of pulls. Okay, how do you like all that? And this is a professional guy, right, who is publishing papers, right? And peer reviewers are proving all this stuff with your money, of course, right? But the inertial mass is also negative. So negative mass still falls down in a gravitational field and moves towards the positive mass. Hence, Einstein's equivalence principle still holds. That's important. If it holds, then we haven't violated Einstein's equivalence principle, right? All matter moves the same way in a gravitational field, regardless of mass, including negative matter. Sounds like science, sounds like physics, rational physics. You know, it's for you to decide whether this has anything to do with rationality anymore, whether this is science, whether this is physics. What is this? This is absolute garbage. That's what it's called. Poppycock. How it got into the, into the so-called scientific literature, or should we be suspecting whether it's scientific anymore? How did it get there? How did peer reviewers approve this garbage? Negative mass and negative time and, warp time and traveling to the past and to the future. What is all this nonsense? If this hasn't shocked you, like Neil Bohr said, then you haven't understood it. Okay, so again, let's put it up there. Yeah, these guys are developing equations with your money, by the way, for all this garbage, including, wormholes, virtual particles, black holes, dark matter, dark energy, whatever nonsense is out there. That's what they're all studying. This whole body of mathematicians is studying all this nonsense that doesn't exist, that's nowhere. It just keep giving you equations, and they can't make any sense of it, so they're kind of like at a crisis because, they cannot explain anymore. Even using, they cannot come up with new ideas. They run out of ideas within this framework. And so you're paying now for them to develop, for leprechauns and unicorns. That's where they're at now. They're playing with spirits, just like the people of old, the religions of old. And so I have a definition for what special relativity is. Specifically, special relativity, not to mention general relativity, string theory, and quantum mechanics, but specifically for special relativity. And here it is. Here's the definition for it. And I think you'll agree with me that this definition says it all. Says exactly what special relativity is. Okay, psychosis is a condition of the mind that results in difficulties determining what is real and what is not real. Okay, I think it passes that test, right? Symptoms may include delusions and hallucinations. Yep, sounds about right? Passes number 2, right? Additional symptoms are disorganized thinking and incoherent speech and behavior that is inappropriate for a given situation. Absolutely. Pass all 3 of them. And dopamine is believed to play an important role. Yeah, I think dopamine is what's happening to all these people at the university level. There's a lot of dopamine going out there. And that's why they come up talking about all this nonsense. And instead of challenging their professors, they all bow down, partly because they need careers, futures. And they say, well, I want to get a job at NASA. If I say that relativity is wrong or quantum is wrong, irrational, I'm not going to get published. I'm not going to get a job. So I'm going to play ball. And that's what everybody's saying out there. And so they all fall into the congregation and they start praying, and they believe what the priest tells them. So we're back to the Dark Ages.